Welcome back to another info index video. Today we'll be looking at some of the basic kinematics equations and how to derive them. Kinematics is a branch of classical mechanics that describes the motion of points, bodies or objects, and systems of bodies or groups of objects without considering the forces that cause them to move. So what does this mean exactly? It means that given some information on certain variables relating to an object, we can predict if and how an object will behave. We will be describing motion related to time, displacement, acceleration, and velocity. Note that time is a scalar, while the other three are vectors. Also note that mass is not one of the above variables, as this is significant. We will first examine the basic equations, then solve some problems related to these equations. As you can see, these equations all solve for a certain variable, while requiring three other variables. This means that as long as three unique variables are known, all other variables can be solved for. Equations are used as they are more versatile and easier to manipulate than graphs. In total, there is a set of 5 equations which can be derived from a velocity versus time graph. The first equation is found by calculating the area under a velocity time graph, or is displacement. As you can see, the displacement, or delta d, is equal to the initial velocity plus the final velocity divided by 2, or that's the average velocity multiplied by the change in time, or delta t. The second equation is constructed by taking the slope of the graph, where a is rise over run and a is acceleration, and a equals to delta v over delta t, or acceleration is equal to change in velocity over time. If you rearrange it, delta v is equal to v2 minus v1, and you get v2 equals to v1 plus at. Now we can manipulate the above 2 equations, or the previous 2 equations, to create 3 more equations. If you substitute the expression for v2 into equation 1 to find equation 3. So again, the expression for v2 is v1 plus at. And if you substitute it into the first equation, you get delta d equals to v1 plus a delta t plus v1 divided by 2, everything multiplied by delta t. And that turns out to get your displacement is equal to initial velocity multiplied by displacement time plus 1/2 the acceleration multiplied by the displacement time squared. To find equation 4, isolate t in equation 2. So this is equation 2, isolate t, and substitute it into equation 1. And you get delta t, or change in time, is equal to v2 minus v1, or final velocity subtract initial velocity, divided by acceleration. And you sub it into equation 1, you get delta d equals to v2 squared minus v1 squared over 2a. And then that turns out to give you v2 squared minus v1 squared plus 2a delta d. To find equation 5, first isolate for v1 in equation 2. Then substitute this in equation 1. Basically, it turns out that displacement is also equal to final velocity multiplied by change in time, subtract half the acceleration multiplied by the change in time squared. Okay, so we're going to do some practice problems to demonstrate how these equations work. So, if Rico starts running with a velocity of 5 meters per second north, and after 10 seconds he is sprinting at 10 meters per second north, how much distance has he covered? Well, we use these equations, d equals to v1 plus v2 over 2, multiplied by time, and delta d is equal to, well, 5 plus 10, because that is his initial and final velocities, and divided by 2, multiplied by time, because it is 10 seconds. So it turns out that the displacement is 75 meters. If Charles starts driving with a velocity of 20 meters per second, and after 5 seconds his velocity is 10 meters per second, what was his acceleration during this time? Okay, so we're given velocity and we're given the change in time. We're given initial and final velocity, and we're trying to find acceleration. So we use v2 equals v1 plus a delta t. And we know that v2 is 10, because after 5 seconds his velocity is 10 meters per second. We know v1 is 20 because that's just a given. And we also know the time because it's after 5 seconds. So we'll isolate for A. And it turns out that acceleration is -2 meters per second squared. Okay, next question. How much time does it take Bill to cover 20 meters with an acceleration of 2 meters per second squared and an initial velocity of 1 meters per second squared? Okay, so we'll use the equation displacement is equal to v1 delta t plus 1/2 acceleration delta t squared. We know that the displacement is 20 meters, we know that the initial velocity is 1 meter per second, and we know that the acceleration is 2 meters per second squared. So we're trying to isolate for t here. So as you can see, we'll simplify it as much as possible, then factor it, and well, you'll get 2 answers if you try to factor it, right? But t must be equal to 4, since time can only be positive in this setting. Okay, if Darrian has an initial velocity of 50 meters per second and decelerates at a rate of 10 meters, maybe I spelled it wrong, oh well, at a rate of 10 meters per second squared over a distance of 120 meters, what is his final velocity? So we'll use the equation v2 squared equals v1 squared plus 2a delta d. We know that the initial velocity is 50 meters per second because that's a given. We know his acceleration is -10 because he is decelerating at a rate of 10 meters per second squared. And we know that the displacement is 120 meters because that's also a given. So we isolate for v2, and well, that's already isolated in the equation, so we'll just take the square root of both sides, and it turns out that v2 is 10 meters per second. Alright, next question. If Alex comes to a complete stop over a distance of 100 meters over 5 seconds, what was his acceleration during this time that caused him to stop? Okay, so we'll use the final equation, delta d equals to v2 delta t minus 1/2 a delta t squared. You should notice that we're given the distance, we're given the time, and basically we're also given another variable, which is the final velocity, although it's not explicitly mentioned in the question. However, the question does state that he comes to a complete stop over a distance of 100 meters over 5 seconds. A complete stop means that his final velocity is actually 0 meters per second. So we'll substitute the displacement as 100 meters, the final velocity is 0 meters per second, and the change in time is 5 seconds, as shown. And we'll isolate for acceleration, and it turns out that acceleration is -8 meters per second squared. So it turns out that most of these problems were whole number answers. When doing other questions, do not be surprised if they contain radicals or fractions. Actually, that's pretty common. Just make sure you're applying the equations correctly. Thank you for watching.